Out there, in the endless black of space, hidden among the swirling galaxies and ancient starlight, something extraordinary is pulsing, a signal so precise it rivals the most accurate clocks on Earth, a beacon from the far reaches of the cosmos. These are pulsars, the universe's natural lighthouses, spinning remnants of dead stars that flash with such regularity you could set your watch by them. But today, we're not just talking about any pulsars, we're venturing to the very edge of what we know, to the most distant ones ever detected, where the rules of physics bend and the mysteries of the universe deepen. What secrets do these far-flung cosmic timekeepers hold? How do they challenge everything we thought we knew about space, time, and the very fabric of reality? Strap in, because we're about to embark on a journey that will stretch your imagination to its limits. Picture this: a star far more massive than our Sun lives out its fiery existence before collapsing in a cataclysmic explosion. What's left behind isn't just a corpse, it's a pulsar, a city-sized sphere of pure, crushed matter spinning hundreds of times per second, shooting beams of radiation across the cosmos like a celestial strobe light. These distant pulsars, some billions of light years away, aren't just scientific curiosities, they're time capsules, carrying messages from the early universe, from epochs so ancient that galaxies were still forming. Their pulses, traveling across unimaginable distances, arrive at Earth as faint whispers, decoded by telescopes that act as cosmic eavesdroppers. What stories do those whispers tell? What can they teach us about the birth of the universe, the nature of dark matter, or even the possibility of other dimensions? This isn't just about distant points of light in the sky, it's about pushing the boundaries of human knowledge. Every pulse from these far-off pulsars is a challenge, a puzzle waiting to be solved. Some spin so fast they defy logic, others flicker in ways that hint at undiscovered physics. And then there are the ones so distant their light has traveled for billions of years just to reach us, carrying with it echoes of a younger, wilder universe. By the time we're done, you'll see the night sky differently, not as a static canvas, but as a living, pulsing frontier, full of unanswered questions and breathtaking possibilities. So let's dive in and uncover 30 astonishing facts about the universe's most distant pulsars, where every discovery rewrites the rules and every pulse brings us closer to understanding the cosmos itself. At the heart of every pulsar lies one of the universe's most extreme creations, a neutron star. These incredibly dense objects are what remain after a massive star explodes in a supernova, crushing its core down to a sphere no bigger than a city, yet packing more mass than our entire sun. Imagine taking all the matter in a skyscraper and squeezing it into a single sugar cube. That's the kind of mind-bending density we're talking about. But what makes neutron stars truly special is when they spin, sending out twin beams of radiation from their magnetic poles like cosmic searchlights. If Earth happens to be in the path of one of those beams, we detect it as a pulse, a flash of light or radio wave so regular it could rival the ticking of an atomic clock. That's why we call them pulsars, short for pulsating stars. Their precision is nothing short of astonishing. Some spin hundreds of times per second, flashing with the kind of consistency that makes even our most advanced human-made clocks look primitive. This incredible regularity isn't just a cosmic curiosity, it's a tool that lets scientists test the very fabric of reality. Einstein's theory of general relativity predicted how massive objects warp space and time, and pulsars provide the perfect way to check if he was right. When a pulsar orbits another massive object, like a black hole or another neutron star, the extreme gravity tugs at spacetime itself, subtly altering the rhythm of the pulses. By tracking these tiny changes, astronomers have confirmed Einstein's predictions with breathtaking accuracy, proving that even a century later, his ideas still hold up under the universe's most extreme conditions. But the story doesn't end there. Pulsars also act as cosmic laboratories for physics we can't recreate on Earth. Their crushing gravity and intense magnetic fields trillions of times stronger than Earth's create environments where matter behaves in ways that defy our everyday experience. Electrons are squeezed into bizarre states, and atoms are crushed into dense nuclear poster. Some pulsars even have mountains, tiny imperfections on their surface just millimeters high, but because of their insane density, those minuscule bumps weigh as much as entire mountain ranges here on Earth. These extreme conditions let scientists probe the boundaries of physics, answering questions about how matter behaves under pressures and forces we could never replicate in a lab. And then there's their role as galactic lighthouses. Because their pulses are so predictable, astronomers can use them like mile markers across the cosmos. By measuring how long it takes a pulse to reach us and how its frequency changes over time, scientists can map the structure of our galaxy, track its rotation, and even detect invisible clouds of gas and dark matter drifting between the stars. Some of the most distant pulsars act like echoes from the early universe, their light traveling for billions of years before finally reaching our telescopes, carrying secrets from a time when galaxies were just beginning to form. Every pulse is a message, a piece of the puzzle, helping us unravel the mysteries of the cosmos one flash at a time. The story of pulsars begins not in the depths of space, but in a humble field in Cambridge, where a young doctoral student named Jocelyn Bell Burnell noticed something peculiar in her radio telescope data. It was 1967, and Bell was sifting through miles of chart paper recordings when she spotted an unusual signal. A series of rapid, rhythmic pulses arriving every 1.337 seconds with such precision they seemed artificial. At first, the team jokingly labeled it LGM, short for Little Green Men, half seriously wondering if they'd stumbled upon a beacon from an alien civilization. But as more of these signals appeared across the sky, the truth became clear. This wasn't an extraterrestrial hello, it was the birth cry of an entirely new cosmic phenomenon. What Bell had discovered was the first known pulsar, later named CP1919 for its coordinates in the constellation Vulpecula. The scientific community was stunned. No one had predicted that collapsed stars could spin so fast or emit such clockwork flashes of radiation. The revelation turned astrophysics on its head. Suddenly, scientists realized that the universe was filled with these ultra-dense, spinning relics, cosmic lighthouses blinking in the darkness. Bell's advisor, Anthony Hewish, would later share the Nobel Prize for the discovery, though her critical role was controversially overlooked at the time, a reminder of the barriers women faced in science. The impact of that moment can't be overstated. Pulsars became instant tools for testing Einstein's theories, mapping the galaxy's magnetic fields, and even probing the interstellar medium, the thin gas between stars. Before Bell's discovery, neutron stars were purely theoretical, and many doubted they could ever be observed. Yet here they were, not just real, but broadcasting their presence across the cosmos. Researchers soon realized that pulsars were nature's gift to astronomy, part timepiece, part particle accelerator, part gravity detector. Their pulses could measure cosmic distances, reveal the presence of invisible planets, and even serve as intergalactic GPS signals for future spacefarers. Bell's story also highlights how science often advances not through eureka moments, but through patient observation and the courage to question the obvious. She nearly dismissed those first pulses as telescope interference, a glitch in the data, but her persistence revealed a universe far stranger and more wonderful than anyone had imagined. Today, we know of thousands of pulsars, each one a reminder that the cosmos is full of surprises, waiting for the next curious mind to uncover them. And it all started with a young scientist, a roll of paper, and a signal so regular it made the world wonder if we were no longer alone. To understand how a pulsar is born, you have to witness one of the most catastrophic events in the universe, a supernova explosion. Picture a star at least 8 times more massive than our Sun, burning through its nuclear fuel over millions of years. As it runs out of hydrogen, then helium, then heavier elements, the star becomes a layered cosmic onion with fusion reactions occurring in shells around its core. But when it finally reaches iron, the star hits a wall. Iron doesn't release energy when fused, it absorbs it, starving the core of the outward pressure that's been holding the star up against its own crushing gravity. In a fraction of a second, the core collapses. Protons and electrons are forced together, merging into neutrons and releasing a flood of neutrinos, ghostly particles that blast outward with the energy of 1,000 suns. The outer layers of the star, now without support, come crashing down at nearly a quarter the speed of light before rebounding off the newly formed neutron core in a shockwave so powerful it outshines entire galaxies. This is the supernova, a detonation visible across the cosmos, scattering the star's enriched guts into space to one day form new stars, planets, even life. What's left behind is a neutron star, a city-sized remnant so dense that a teaspoon of its material would weigh 1 billion tons on Earth. But not all neutron stars become pulsars. The key is spin. Just like an ice skater pulling their arms in to rotate faster, the collapsing star's core speeds up dramatically as it shrinks. A star that might have rotated once every few weeks in its prime now spins hundreds of times per second, its magnetic field amplifying to mind-bending strength. These magnetic poles don't align with the rotation axis, creating a lighthouse effect as beams of radiation sweep across space with every turn. If Earth lies in the path of those beams, we see the rhythmic flashes that define a pulsar. The violence of this birth leaves pulsars with extraordinary properties. Some, called millisecond pulsars, rotate faster than a kitchen blender, their surfaces moving at a significant fraction of light speed. Others have magnetic fields so intense they could strip the data from a credit card halfway to the moon. And because they're born from collapse, their spin rates and magnetic fields are imprints of their formation, cosmic fingerprints telling the story of their explosive origins. This transformation from dying star to spinning beacon is so extreme it challenges our understanding of matter itself. Under such pressures, atoms cease to exist as we know them. Electrons are crushed into protons, forming a sea of neutrons so tightly packed they behave like a single quantum fluid. The pulsar's crust, only a kilometer thick, is likely the strongest material in the universe, a crystalline lattice of atomic nuclei deformed into bizarre shapes scientists poetically call nuclear pasta. And at the center, conditions are so extreme that neutrons may dissolve into a soup of quarks, a state of matter impossible to recreate in any lab on Earth. Every pulsar pulse we detect is a direct line back to this moment of cosmic alchemy, where ordinary matter is forged into something extraordinary. The supernova's fury doesn't just create a new object, it rewrites the rules of physics, leaving behind a spinning, flashing tombstone marking where a star once lived and died. Think of a lighthouse on a stormy coast, its beam cutting through the darkness in a steady rhythm. Now imagine that same principle playing out on a cosmic scale, with a pulsar's magnetic poles acting like the lamp and its rapid spin turning it into nature's most precise strobe light. Here's how it works. When a neutron star forms, its magnetic field doesn't vanish, it gets compressed and amplified, becoming trillions of times stronger than Earth's. But here's the twist. Those magnetic poles rarely align with the star's axis of rotation. Instead, they're tilted like a wobbly top spinning at dizzying speeds. As the pulsar rotates, these misaligned magnetic poles whip beams of radiation, radio waves, X-rays, or even gamma rays through space like cosmic searchlights. If Earth happens to lie in the path of one of those sweeping beams, we detect it as a pulse, a flash of energy so regular it could set your watch. But here's the catch: we only see the pulsar if its beam crosses our line of sight. Countless others might be spinning silently in the darkness, their light never reaching us, like lighthouses whose beams sweep across empty ocean. This lighthouse effect explains why some pulsars seem to vanish over time. As they age, their spin slows and the beams may drift out of alignment with Earth. Others, called intermittent pulsars, flicker on and off as their magnetic fields twist and reconfigure, temporarily cutting off the flow of radiation. There's even a rare class known as nulling pulsars that suddenly go silent for hours or days before abruptly restarting, as if someone flipped a switch. The angle of those beams also holds clues to a pulsar's history. Younger pulsars often have wider beams, sweeping broad arcs across space, while older ones narrow over time as their spin slows. Some beams are so tightly focused that if you stood on a planet orbiting one, you'd experience brief, blinding flashes of radiation separated by stretches of utter darkness. But the real magic happens when these beams interact with their surroundings. Some pulsars plow through clouds of interstellar gas, their beams ionizing the material and creating glowing trails light years long. Others, nestled in supernova remnants, light up the debris around them like a flashlight in fog. And in binary systems where a pulsar orbits another star, its beams can strip material from its companion, creating swirling disks of superheated plasma that flicker in sync with the pulses. This sweeping dance of light isn't just beautiful, it's a goldmine for scientists. By studying how the pulses change over time, astronomers can map the pulsar's magnetic field, measure its wobble, and even detect planets orbiting it. In some cases, the beams act like cosmic scanners, revealing details about the interstellar medium they pass through. Every flicker, every pause, every shift in frequency is a piece of data, helping us decode the universe one pulse at a time. So the next time you hear about a pulsar's steady beat, remember, we're only hearing the ones shouting in our direction. The cosmos is full of these spinning beacons, their light sweeping through the void in an endless, silent rhythm, most of it unseen, a reminder of how much lies hidden just beyond our view. Determining the distance to a pulsar isn't like measuring the space between cities on a map. It's more like trying to clock the location of a strobe light flashing somewhere in a hurricane. But astronomers have cracked this cosmic puzzle using two brilliant tricks hidden in the pulsars themselves: timing and dispersion. Here's how it works. Every pulse from a spinning neutron star arrives at Earth like a metronome ticking across the universe. But as that signal travels through space, it doesn't move through a perfect vacuum. Thin clouds of ionized gas, the interstellar medium, slow down certain radio wavelengths ever so slightly, like light bending through water. This effect, called dispersion, means higher frequency waves hit our telescopes a fraction of a second before lower ones. The longer the journey, the more pronounced this delay becomes. By precisely measuring this smear across frequencies, scientists can calculate how much material the signal has passed through, giving them a cosmic yardstick to estimate the pulsar's distance. But that's only half the story. Pulsar timing takes this even further, exploiting Einstein's theory of relativity in action. When a pulsar orbits another massive object, say a white dwarf or black hole, the extreme gravity subtly warps the fabric of space-time, causing minuscule variations in the pulse arrival times. By tracking these deviations over years with atomic clock precision, astronomers can reconstruct the pulsar's motion and position in 3D space, like celestial cartographers triangulating coordinates from the echoes of a spinning beacon. The most distant pulsars reveal their locations through these painstaking measurements, some so far that their light has traveled for billions of years before reaching us. What's astonishing is how accurate these methods are. Take the pulsar J034 plus 0543, located approximately 2,500 light-years away. By analyzing dispersion and timing, scientists pinned down its distance to within 1%, like measuring the width of a hair from 3 miles away. These techniques don't just map individual pulsars, they've revolutionized our understanding of the Milky Way's structure. When combined with data from spacecraft like Gaia, which measures stellar parallax, pulsar distances help astronomers construct a three-dimensional model of our galaxy's spiral arms, magnetic fields, and even the distribution of invisible dark matter. The real magic happens when these measurements reveal cosmic oddities. Some pulsars appear to be racing through space at breakneck speeds, their high velocity betraying a violent birth where the supernova explosion kicked them like a gravitational slingshot. Others drift lazily, tracing the gentle currents of the galaxy's rotation, and a few, like the millisecond pulsar PSRB 1937+21, are so distant they act as probes of the intergalactic medium itself, their signals passing through multiple galaxies before reaching us. Each pulse is a message in a bottle, carrying encoded details about every cloud, magnetic field, and dark matter halo it encountered along the way. This isn't just academic curiosity, it's practical science. Precise pulsar distances allow us to test fundamental physics, like variations in the gravitational constant or the presence of hypothetical dark matter particles. They've even been proposed as navigation beacons for future interstellar travel, a cosmic GPS where millisecond variations in pulse arrival times could pinpoint a spacecraft's position anywhere in the galaxy. So when you hear about a pulsar flickering from the edge of the observable universe, remember, that steady beat is more than a cosmic curiosity. It's a ruler, a clock, and a roadmap all in one, helping us measure the immeasurable depths of space. Deep in the constellation Cassiopeia, a tiny point of light flickers with a secret. It holds the title of the most distant pulsar ever detected. Known as PSR J0002+6216, this cosmic beacon lies an astonishing 7,500 light-years from Earth, so far that its radio pulses take longer to reach us than all of recorded human history. What makes this particular pulsar extraordinary isn't just its distance, it's the way it moves. Scientists tracking its pulses noticed something bizarre. It's racing through space at nearly 3 million miles per hour, fast enough to cross the distance between Earth and the Moon in just 10 minutes. That kind of speed doesn't just happen by accident. This pulsar's breakneck velocity tells a violent origin story. Most neutron stars inherit a gentle drift from their parent star's motion, but PSR J0002+6216 got a catastrophic kick, likely from an asymmetric supernova explosion that launched it like a cosmic cannonball. Supporting this theory is the long, comet-like tail of energized particles stretching 14 light-years behind it, visible in X-rays, tracing its path back to the heart of a supernova remnant. It's as if the universe left us a glowing arrow pointing directly to the scene of the crime. But the real shock came when researchers calculated its trajectory. Unlike most pulsars, which meander through the galaxy's spiral arms, this one is on an escape route barreling toward intergalactic space at a speed that will eventually fling it clear of the Milky Way entirely. That makes it a rogue pulsar, destined to drift forever in the emptiness between galaxies, its pulses fading into the void with no one left to hear them. Detecting something this distant and fast required ingenuity. Traditional pulsar surveys often miss objects like this because their signals stretch and distort as they traverse vast stretches of interstellar gas. The breakthrough came when astronomers combined data from multiple radio telescopes, using a technique called very long baseline interferometry to piece together its faint whispers like a cosmic jigsaw puzzle. The effort paid off with a discovery that challenges our understanding of supernova mechanics. Why does this matter? Pulsars like PSR J0002+6216 are nature's extreme physics labs. Its speed suggests that supernova can be far more lopsided than models predicted, potentially due to turbulent instabilities in the collapsing star's core. Some theorists even speculate that such kicks could arise from hidden forces, like asymmetric neutrino emission or gravitational waves carving a path through spacetime. Every pulse from this distant sprinter carries clues about the most violent events in the universe and the invisible laws that govern them. For now, it remains a solitary traveler, a runaway remnant of a star that died long before the pyramids were built. Yet each time its signal reaches Earth, it offers a fleeting glimpse into the chaos of creation, proving that even on the farthest edges of what we can observe, the cosmos never stops surprising us. Among the universe's most precise natural instruments, pulsars have an unexpected superpower. They act as galactic-scale gravitational wave detectors. Here's how it works. When gravitational waves ripple through space-time, they stretch and compress the fabric of the cosmos ever so slightly, altering the distances between objects. Normally, these distortions are too minuscule to measure, but pulsars offer a workaround. Their clock-like pulses arrive on Earth with such predictable regularity that even nanosecond deviations can betray the passage of a gravitational wave. Imagine dropping a pebble into a still pond. The ripples distort reflections on the water's surface. Pulsar timing arrays use the same principle, treating our galaxy as the pond and distant pulsars as fixed reference points. The real breakthrough came when scientists realized they could turn entire collections of pulsars into a galaxy-sized observatory. By monitoring dozens of millisecond pulsars, some spinning hundreds of times per second, across the Milky Way, astronomers created a network so sensitive it could detect space-time distortions smaller than an atomic nucleus across light-years of distance. These pulsar timing arrays don't just sense gravitational waves, they pinpoint their sources. When a wave passes through, it briefly shifts the arrival times of pulses from different pulsars in predictable patterns, like buoys bobbing in sequence on ocean swells. The most distant pulsars in these arrays are especially valuable. Their signals travel longer paths through spacetime, making them more susceptible to gravitational distortions, acting like ultra-sensitive antennas tuned to the universe's lowest frequencies. What they've detected is astonishing. In 2021, after 15 years of data collection, researchers found evidence of a background hum of gravitational waves, likely caused by the slow-motion collisions of supermassive black holes at the centers of distant galaxies. These waves have wavelengths so long spanning light-years that no Earth-based detector could ever sense them. But pulsars, flashing their steady beats across millennia, caught the whispers of these cosmic titans circling each other in the void. This technique has opened an entirely new window onto gravitational wave astronomy. Traditional detectors like LIGO catch high-frequency waves from stellar mass black hole mergers, violent, transient events that last seconds. Pulsar arrays, by contrast, sense the deep bass notes of the cosmos, waves from mergers that might take millions of years to complete, imprinting their signature on the steady tick of spinning neutron stars. Future observations may reveal even wilder phenomena: cosmic strings from the early universe, phase transitions in the quark-gluon plasma, or vibrations from extra dimensions predicted by string theory. The implications stretch beyond astrophysics. By comparing pulsar timing data with information from other gravitational wave detectors, scientists are testing whether gravity behaves exactly as Einstein predicted over cosmic scales. Some theories suggest gravity might weaken or behave differently across vast distances. Pulsar arrays could catch these subtle deviations. There's even speculation that advanced civilizations might one day use pulsar timing to navigate interstellar space, treating these natural clocks as waypoints in a galactic positioning system. Every pulse from these distant sentinels carries more than just timekeeping. It's a snapshot of spacetime itself, a ripple in the cosmic pond that reminds us the universe is far more dynamic than it appears. As our timing precision improves, who knows what other whispers from the fabric of reality will uncover? Some of the fastest objects in our galaxy aren't sleek spaceships or rogue planets, they're pulsars, hurtling through space at speeds that defy imagination. Take PSRB 2224 + 65, for example. This cosmic speedster races through the Milky Way at nearly 2 million miles per hour, so fast it could cross the distance from Earth to the Moon in just under 20 minutes. But what could possibly launch a city-sized ball of crushed star matter at such insane velocity? The answer lies in the violent chaos of its birth. When a massive star goes supernova, the explosion isn't always symmetrical. If one side of the collapsing core gets a stronger kick than the other, the newborn pulsar rockets away like a bullet fired from a cosmic gun, carrying the recoil of its own creation. These pulsar speed demons don't just move fast, they leave destruction in their wake. As they barrel through interstellar space, their powerful magnetic fields and intense radiation smash into surrounding gas clouds, creating vast shockwaves called cosmic bow shocks. Picture a speedboat tearing through calm water, throwing up a curved wall of spray at its bow. Only here, the boat is a million-degree neutron star, and the spray is a glowing arc of particles stretched light years across space. The most dramatic example might be the Guitar Nebula, sculpted by Pulsar PSRB 2224+65 supersonic flight. Its bow shock forms a glowing string-like structure 37 trillion miles long, with vibrating ripples that eerily resemble sound waves frozen in gas and dust. What's truly mind-bending is how these pulsars navigate the galaxy. Unlike stars that gently orbit the Milky Way center, these runaway neutron stars often take wild, hyperbolic paths. Some are even on escape trajectories that will eventually fling them into the void between galaxies. Their speed offers forensic clues about their origins. Pulsars moving at more than 1 million miles per hour likely got an extra boost from binary companions. Their explosive births might have occurred in tight orbits where the supernova's sudden mass loss catapulted them like a slingshot. Others might have been accelerated by the intense gravitational pull of dense star clusters, where close encounters with other massive objects act like cosmic pinball bumpers. But the real surprise, some of these speed demons shouldn't exist at all. According to conventional models, a pulsar moving too fast would tear apart its own magnetic field, yet we've observed several that defy this limit. One theory suggests they might be born fast, their initial spin somehow converting rotational energy into straight-line velocity. Others speculate that hidden physics, perhaps interactions with dark matter, could be giving them an extra push. Whatever the explanation, each hypervelocity pulsar forces us to rethink what's possible in the extremes of astrophysics. Their breakneck journeys also make them invaluable cosmic probes. As they plow through different regions of interstellar space, their bow shocks light up the invisible, revealing the density of gas clouds, the strength of magnetic fields, and even the presence of dark matter halos. Some pulsar wakes have been found tracing paths through otherwise undetectable filaments of the galaxy's hidden structure, like glowing footprints in the dark. So while these cosmic speedsters might seem like outliers, they're actually messengers reminding us that the universe is far more dynamic, more violent, and more surprising than we often assume. Every hypervelocity pulsar is a fossil record of its own cataclysmic birth, a high-energy explorer charting unseen frontiers, and a natural particle accelerator pushing matter to extremes we can't replicate on Earth. And somewhere out there, another one is racing through the void, waiting for us to catch its signal, and with it, the next clue about how the universe really works. Deep inside a pulsar's crushing core lies a realm where physics textbooks get rewritten. At pressures 100 trillion times greater than Earth's atmosphere and densities where a sugar cube's worth of material would outweigh Mount Everest, matter stops behaving normally, it mutates. Scientists suspect these extreme conditions rip apart the familiar structure of neutrons themselves, dissolving them into a swirling soup of quarks and gluons, the fundamental building blocks that normally remain forever locked inside particles. This theoretical state, called quark-gluon plasma, is nature's ultimate alchemy, a form of matter that hasn't existed freely since the first millionth of a second after the Big Bang. What makes this so revolutionary? Under everyday conditions, quarks are permanently confined by the strong nuclear force. You'll never find one alone, just as you'll never squeeze a single drop from the ocean. But in a pulsar's core, the pressure becomes so intense that this rule breaks. Quarks might flow freely like liquid metal, or arrange themselves into bizarre crystalline patterns theorists whimsically dub quark stars. Some models even suggest stranger possibilities, color superconductors, where quarks pair up and flow without resistance, or strange matter containing exotic particles not seen anywhere else in the universe. These aren't just theoretical curiosities. If such states exist, they could be more stable than ordinary matter, meaning a single chunk could theoretically convert anything it touches into strange matter. A cosmic domino effect with profound implications. Clues to this exotic interior come from unexpected pulsar behaviors. Some exhibit glitches, sudden speed-ups in rotation where the star might spin hundreds of times faster before settling back down. One leading explanation: the superfluid neutrons in the star's interior occasionally unlock and transfer angular momentum to the crust like a hidden engine kicking into gear. Even more telling are pulsars with masses approaching or exceeding twice the Sun's, so dense that neutron degeneracy pressure alone shouldn't prevent collapse into a black hole. Their very existence hints at unknown forces at work, possibly quark interactions providing extra support against gravity's relentless crush. The wildest predictions involve hybrid stars, objects with neutron-rich crusts enveloping quark matter cores like cosmic jawbreakers. In these objects, phase transitions might create rippling density boundaries, generating gravitational waves detectable across the universe. There's even speculation about quark novas, cataclysmic events where a neutron star's core abruptly collapses into quark matter, triggering a secondary explosion brighter than a supernova. While no definitive observation confirms these ideas yet, upcoming gravitational wave observatories could soon spot the telltale tremors of quark matter rearranging itself inside distant pulsars. What's exhilarating is how these theories bridge particle physics and astronomy. Laboratories like CERN recreate quark-gluon plasma in fleeting, microscopic quantities during high-energy collisions. But pulsars offer nature's own permanent particle accelerators, city-sized laboratories where these extreme states persist for billions of years. By studying how pulsars pulse, cool, and occasionally quake, we're essentially running diagnostics on matter pushed beyond all known limits. Every irregularity in their steady beats might carry encrypted messages about physics we've yet to discover, a reminder that the universe's rulebook doesn't end with what we've learned on Earth. In the early 1990s, astronomers hunting for pulsars made a discovery that rewrote the textbooks: not a new kind of star, but something far stranger: planets orbiting the corpses of dead stars. The first of these bizarre worlds was found circling PSRB 1257+12, a pulsar roughly 2,300 light-years away in the constellation Virgo. Its existence defied all expectations. After all, how could anything survive the apocalyptic violence of a supernova, the very event that creates pulsars? Yet there they were, not just one, but three small, rocky worlds dancing around this spinning stellar remnant, their presence betrayed by minuscule wobbles in the pulsar's otherwise flawless rhythm. This discovery shattered assumptions about where planets could form. Conventional wisdom held that planets were born in the gentle disks of gas and dust around young stars, not the radioactive wreckage left after a stellar explosion. The leading theory suggests these pulsar planets might be second-generation survivors. When the original star exploded, the blast could have stripped a companion star down to its core, leaving behind debris that coalesced into new worlds. Alternatively, the supernova might have flung existing planets into wild new orbits, only for some to be recaptured by the pulsar's gravity. There's even a tantalizing possibility that these planets formed from the ashes of the dead star itself, a cosmic phoenix rising from the ruins. What's astonishing is how they were found. Unlike traditional planet hunting methods that rely on watching stars dim as planets pass in front, pulsar planets reveal themselves through timing. Every time a planet tugs on its pulsar host, the star's ultra-precise pulses arrive at Earth a fraction of a second early or late. By mapping these deviations over months, astronomers can reconstruct the planet's masses and orbits with incredible precision. In the case of PSRB 1257+12, the data revealed 3 worlds, one slightly larger than Earth's moon, another 4 times our planet's mass, and a third about twice as massive. But the real shock, one of these planets orbits at nearly the same distance from its pulsar as Mercury does from our Sun. Imagine a world bathed not in sunlight, but in deadly X-rays and particle winds, its skies lit by the pulsar's eerie, strobing glow. The surface would be bombarded by radiation intense enough to strip away any atmosphere, if it ever had one. And yet, despite these hellish conditions, the very existence of these worlds proves that planets can form in environments we once thought impossible. Since that first discovery, other pulsar planets have emerged, each more puzzling than the last. Some orbit in bizarre, elongated paths, while others exist in systems where multiple pulsars whirl around each other, creating gravitational labyrinths. There's even speculation about exotic forms of life that could theoretically exist on pulsar planets, not carbon-based like ours, but organisms built from radical chemistry thriving in the particle storms. These finds aren't just curiosities, they're forcing us to rethink how planetary systems are born, evolve, and sometimes cheat death. If planets can form around stellar corpses, then the galaxy might be littered with worlds we never thought to look for hidden survivors clinging to the darkest, most violent corners of space. And every new pulsar planet discovered whispers the same tantalizing question. If they exist here, where else might we find the impossible? Imagine a spaceship hurtling between the stars with no maps to guide it, just the steady, rhythmic flashes of distant pulsars lighting its way like cosmic street lamps. This isn't science fiction, it's a real navigation system scientists have proposed, one that could work anywhere in the galaxy. The concept hinges on a simple but brilliant idea. Pulsars are nature's most perfect clocks, their pulses so regular that over decades they rival the precision of atomic clocks on Earth. By tracking the arrival times of these pulses from multiple pulsars, a spacecraft could triangulate its position with astonishing accuracy, even light years from home. Here's how it would work in practice. Each pulsar's unique fingerprint, its spin rate, pulse shape, and location in the sky, acts like a celestial ID tag. A ship's computer would compare the expected arrival times of pulses from at least 3 known pulsars with the times they're actually detected on board. Even tiny discrepancies, nanosecond delays or advances, would reveal the spacecraft's exact location in 3-dimensional space. It's like GPS, but instead of relying on satellites, it taps into a network of spinning neutron stars scattered across the Milky Way. The European Space Agency has already tested a stripped-down version of this technology with their experiments on the International Space Station, proving the concept works even near Earth. But the real magic happens in interstellar space. Unlike radio beacons or star maps, which grow fainter with distance, pulsar navigation becomes more reliable the farther you travel. Their signals penetrate dust clouds and cross galactic distances with minimal distortion, and their immutable rhythms mean they'll still be ticking billions of years from now. Future explorers could use them to chart courses through uncharted nebulae or even navigate near the supermassive black hole at our galaxy's center, where conventional star tracking might fail. Some proposals even suggest encoding pulsar data into spacecraft's autonomous systems as a fail-safe. If all else fails, listen to the pulsars. The most advanced version of this idea, called XNav X-ray navigation, would use pulsars emitting X-rays rather than radio waves. X-rays travel through space with less interference, and their shorter wavelengths allow for even finer timing precision. A nicer experiment aboard the ISS has demonstrated this with millisecond pulsars, achieving position fixes accurate to within 5 kilometers. In space, that's like pinpointing a needle in a cosmic haystack. For interstellar missions, that precision could mean the difference between sailing smoothly past Alpha Centauri or drifting helplessly into the void. What's astonishing is that we're not just theorizing, we've already sent a pulsar map into the cosmos. The plaques aboard the Pioneer probes and the golden records on Voyager include a diagram showing Earth's location relative to 14 nearby pulsars, their spin rates coded in binary. It's a message to any civilization that might find them. Here's how we navigate the stars. Whether humans or aliens, any technologically advanced species would recognize these pulsing beacons as universal landmarks. This elegant solution to deep space navigation reveals something profound about how we explore. The universe provides its own signposts, we just have to learn to read them. And as our ambitions stretch beyond the solar system, pulsars may become the lighthouses that guide humanity's first steps into the interstellar dark. Among the galaxy's most sinister cosmic relationships are the so-called Black Widow pulsars, spinning neutron stars that slowly devour their stellar companions in a deadly dance of radiation and gravity. Named after the infamous spider that consumes its mate, these pulsars blast their binary partners with such intense beams of energy and particles that they literally vaporize them over millions of years, leaving behind nothing but cosmic dust. Take PSRB 1957+20, one of the first Black Widow pulsars discovered. This millisecond pulsar spins nearly 600 times per second, its beams cooking its companion, a small star roughly 1% the mass of our Sun, with a relentless torrent of gamma rays and charged particles. The energy is so extreme that it strips away the star's outer layers at a rate of about 1 Earth mass every million years, creating a glowing cloud of ionized gas that trails behind the binary pair like a ghostly veil. But the horror doesn't stop there. The pulsar's gravity is so strong that it distorts its companion into a teardrop shape, locking it in a gravitational embrace that ensures one side always faces the neutron star's deadly radiation. This tidal locking creates a horrifying scenario where the star's sunward side is continuously blasted away while the cooler, shadowed side struggles to hold onto its material. Over time, the companion star is whittled down to a cinder, its mass siphoned away until nothing remains but a planetary mass remnant, or worse, complete annihilation. What's even stranger is how these systems form. Most Black Widow pulsars started as more ordinary binaries, where the neutron star's intense gravity pulled material from its companion, a process that actually spun the pulsar up to insane speeds. But as the pulsar grew stronger, its radiation pressure became so powerful that it reversed the flow. Instead of feeding on its partner, it began vaporizing it. Some pulsars have even been caught in the act, their companions visibly puffing away under the onslaught, their outer layers expanding into distorted, comet-like tails visible in ultraviolet light. These cosmic predators challenge our understanding of stellar evolution. Conventional models suggest binary stars should either stabilize or merge, but Black Widow pulsars defy expectations by existing in a gruesome equilibrium. Their companions just massive enough to keep feeding the pulsar's rotation, but not so massive that they're quickly destroyed. It's a balancing act between destruction and survival, one that leaves astronomers wondering how many similar systems might be lurking undetected in the galaxy. Yet for all their violence, Black Widow pulsars are also laboratories for extreme physics. The interactions between their radiation and the evaporating companion create conditions impossible to replicate on Earth: particle acceleration at energies far beyond our largest colliders, magnetic reconnection events that dwarf solar flares, and plasma dynamics that could unlock secrets about interstellar material. Some even emit mysterious, sporadic bursts of radio waves that hint at poorly understood processes in their magnetospheres. the fate of these systems is written in their pulses. As the companion star dwindles, the pulsar's spin will gradually slow, its beams fading into silence. But until then, they remain some of the most dramatic examples of the universe's brutality, a reminder that even among the stars there are predators and prey. And somewhere out there, another companion star is burning away under the relentless gaze of its pulsar partner. Its death throws lighting up the cosmos in ways we're only beginning to understand. Here's something that bends the mind: some of the oldest pulsars in the universe don't look their age. In fact, many appear shockingly young, their vibrant energy belying billions of years of cosmic history. The reason: relativity and speed. When a pulsar rockets through space at a significant fraction of light speed, time itself warps around it, slowing its aging process relative to the rest of the universe. Imagine two identical twins. One stays on Earth while the other boards a starship traveling near light speed. Upon returning, the traveler would have aged far less than their Earth-bound sibling. Pulsars experience this same time dilation effect, but on a galactic scale. Take Pulsar J003 plus 0745, a pulsar streaking through the Milky Way at over 2 million miles per hour. From our perspective, its pulses arrive precisely, its magnetic field still crackling with intensity, traits typical of a neutron star just a few million years old. Yet its trajectory traces back to a supernova remnant nearly 1 billion years old. How does this paradox unravel? The answer lies in Einstein's special theory of relativity. At such extreme velocities, time for the pulsar ticks slower compared to stationary observers like us. While the universe aged 1 billion years, the pulsar's internal clock might have measured only a fraction of that, preserving its youthful vigor. But speed isn't the only factor distorting appearance. Doppler boosting plays a role too. As a pulsar races toward us, its beams of radiation get compressed, shifting to higher frequencies and appearing brighter, like the rising pitch of an approaching ambulance siren. This amplification can make distant, ancient pulsars masquerade as nearby youngsters in telescope data. Conversely, those moving away dim and redden, sometimes vanishing from detection entirely. It's a cosmic game of hide and seek, where what we see depends entirely on perspective. The implications are profound. Astronomers must untangle these relativistic effects to calculate true ages, especially for hypervelocity pulsars flung from galactic collisions or supernova kicks. Some might even be intergalactic interlopers, their journeys spanning epochs yet their pulses crisp as new. These time-warped wanderers challenge our assumptions about stellar life cycles, proving that in the cosmos, age really is just a number, and sometimes the oldest actors shine brightest. Even the most precise cosmic clocks sometimes stutter, and when a pulsar suddenly speeds up for no apparent reason, astronomers call it a glitch. These mysterious events can warp a neutron star's spin rate by fractions of a second, or, in extreme cases, send it whirling hundreds of rotations faster almost instantaneously. The record holder, Pulsar J0835-4510, once accelerated by an astonishing 1 part in 10,000, the equivalent of Earth's day, shortening by 2 seconds without warning. What could possibly cause such bizarre behavior in objects otherwise known for their perfect regularity? The answers lie buried deep beneath a pulsar's crust, where the rules of physics twist into something unrecognizable. One leading explanation points to Starquake's cosmic-scale tremors rippling through the neutron star's ultra-dense surface. Picture the pulsar's crust as a rigid shell floating atop an ocean of superfluid neutrons. As the star gradually slows over millennia, its crust stiffens and fractures like drying clay, suddenly collapsing inward by mere millimeters. But in a neutron star where density warps gravity, that tiny movement releases enough energy to jolt the entire star's rotation. The 2004 discovery of Pulsar J0537-6910's glitch provided compelling evidence. X-ray telescopes caught its surface temperature spiking precisely as its spin accelerated, mirroring what models predicted for crustal fractures. But starquakes aren't the only suspect. Dive deeper, past the crust into the neutron superfluid core, and you'll find vortices swirling like microscopic tornadoes. In normal conditions, these vortices remain pinned to the crust, spinning in sync. But when they suddenly unpin and surge outward, they transfer angular momentum like a skater pulling their arms in, revving up the star's rotation. The 2016 Christmas glitch of Pulsar B2334+61 offered a smoking gun. Its two-stage speed-up matched superfluid models perfectly. First a sudden jump from vortex release, then a gradual rise as the superfluid and crust recoupled. Some glitches defy both explanations, hinting at even wilder physics. The Vela Pulsar, one of the most active glitches, occasionally produces anti-glitches where it slows down instead. Then there's Pulsar J1841-050, which not only sped up but permanently changed its pulse shape, as if something massive shifted inside, realigning its magnetic field. Theorists speculate these outliers might involve quark matter rearrangements or magnetic explosions in the core, where pressures are so extreme that neutrons dissolve into subatomic soup. What makes glitches invaluable is how they serve as X-rays into a pulsar's hidden interior. Each event leaves behind fingerprints, thermal signatures, timing residuals, gravitational wave emissions that let scientists map regions no telescope could ever see. Recent observations even suggest glitches might correlate with fast radio bursts, raising the electrifying possibility that these tiny stellar hiccups could power some of the universe's most energetic phenomena. So while glitches might disrupt a pulsar's perfect rhythm, for astronomers, they're music to the ears, a cacophony of clues ringing from the heart of matter pushed beyond breaking point. Every sudden speed-up is a message in a bottle, washed ashore from a realm where the very fabric of reality gets rewritten. And with each one decoded, we come closer to answering the ultimate question: what exactly happens inside nature's most impossible objects? In the constellation Serpens, a pulsar named Pulsar J1719-1438 spins silently, its rhythmic pulses masking one of the universe's most extravagant secrets, a companion planet that might be the galaxy's largest diamond. Discovered in 2011, this system defies all expectations of celestial chemistry. The pulsar's partner, once a white dwarf star, has been stripped down to a crystalline remnant so dense and carbon-rich that under its crushing gravity, the material could have crystallized into a planet-sized gem. Here's how this cosmic jewel formed. Originally, the pulsar and its companion orbited each other as a binary system. Over eons, the pulsar's gravity siphoned away nearly all of the white dwarf's outer layers, leaving behind a core roughly the size of Jupiter but with 40% more mass. The intense pressure inside this remnant, estimated at millions of times Earth's atmosphere, compresses the carbon into a lattice so tightly packed it likely formed diamond. Not the delicate gemstones we mine on Earth, but a monstrous, ultra-dense crystal structure spanning thousands of miles, glittering under the pulsar's deadly glare. What makes this system even stranger is its improbable survival. Most pulsar companions are either fully evaporated or locked in destructive embraces, yet this diamond planet orbits at a precise distance, just 600,000 kilometers, closer than the Moon is to Earth, maintaining a fragile equilibrium. The pulsar's beams don't vaporize it. Instead, they bathe it in radiation that might make its surface sparkle with auroras of charged particles, like cosmic lightning reflecting off a diamond facet. Astronomers detected this planetary oddity through pulse timing variations, the same method used to find other pulsar worlds. But unlike those discoveries, the data here revealed an object with bizarrely low mass for its size, suggesting a composition unlike any conventional planet. Follow-up observations showed its density matched crystallized carbon, with traces of oxygen that might have seeped into the diamond matrix like impurities in a natural gem. The implications are as dazzling as the discovery itself. If such carbon-rich worlds exist around pulsars, they could be remnants of ancient stars that never fully collapsed into black holes or neutron stars, stellar ghosts frozen into crystalline form. Some theorists speculate these planets might even harbor exotic carbon phases beyond diamond, like metallic hydrogen or superconductive layers deep beneath their surfaces. Yet the most haunting question remains: what would it be like to stand on such a world? Picture a landscape where the ground shimmers with fractal patterns, where mountains might be faceted like cut jewels, and where the sky pulses with lethal radiation from the neutron star above. There's no atmosphere to scatter light, no erosion to dull the crystal plains, just a dead, glittering monument to a star's violent demise. Pulsar J1719-1438 and its diamond planet stand as a testament to the universe's alchemy, where destruction and beauty collide. It's a reminder that even in death, stars can create wonders beyond imagination, worlds where the line between astrophysics and mythology blurs into something truly extraordinary. Hidden in the steady pulse of these cosmic beacons might lie clues to one of astronomy's greatest mysteries: dark matter. While pulsars are known for their precision, some exhibit tiny, unexplained anomalies in their spin rates or energy outputs that don't fit conventional models. Scientists now suspect these irregularities could be the fingerprints of invisible dark matter particles interacting with the neutron star's unimaginably dense material. The theory hinges on a bold idea. If dark matter exists as weakly interacting massive particles WIMP, they could accumulate in pulsars over billions of years, drawn by the star's intense gravity. Over time, these particles might collide and annihilate in the pulsar's core, releasing energy that subtly alters its spin or thermal emissions. Imagine a hidden furnace burning inside the star, its heat barely perceptible but enough to disrupt the pristine rhythm astronomers expect. Some researchers even propose that certain pulsars, especially those in regions dense with dark matter like galactic centers, could act as natural detectors, their tiny rotational hiccups betraying the presence of otherwise invisible particles. One tantalizing candidate is Pulsar J1745+1017, a pulsar near the Milky Way's core whose timing residuals show peculiar periodic deviations. While ordinary explanations like planetary companions or magnetic field shifts can't fully account for these anomalies, dark matter interactions could. Calculations suggest that if WIMP cluster in the pulsar's core, their annihilation could generate enough heat to temporarily soften the superfluid interior, causing the star to speed up infinitesimally, exactly the kind of glitch observed. But pulsars might reveal dark matter in even stranger ways. Some models predict that dense neutron stars could capture and compress dark matter to the point where it collapses into miniature black holes, sparking detectable gravitational waves or sudden X-ray bursts. Others speculate that certain pulsar beams passing through dark matter halos could scatter in telltale patterns, like a flashlight shining through fog. The search is far from conclusive, but each anomalous pulsar brings us closer to answers. Whether through timing irregularities, thermal excesses, or unexpected emissions, these cosmic clocks might be ticking down to a revolutionary discovery. One where the universe's most elusive substance finally betrays its presence through the very objects it helps shape. Deep in the constellation Vulpecula, a pulsar named Pulsar B 1931+24 defies all expectations. It doesn't just pulse, it plays dead. For years at a time, this so-called zombie pulsar abruptly stops emitting radio waves, vanishing from telescopes as if someone flipped a switch. Then, just as mysteriously, it roars back to life, its pulses returning with perfect precision as though nothing happened. This bizarre on-off behavior, repeating in cycles lasting roughly 35 days active and 25 days silent, makes it one of the most enigmatic objects in the galaxy. What could possibly cause a spinning neutron star, a beacon of cosmic regularity, to flicker like a faulty light bulb? The leading theory involves a cosmic tug of war between the pulsar's magnetic field and its surrounding environment. Normally, a pulsar's intense magnetic field acts like a dynamo, accelerating particles that create its characteristic beams. But Pulsar B 1931 plus 24 might be teetering on a knife's edge between two states. When on, its magnetic field is strong enough to sustain the particle flow needed for pulses. When off, the system could collapse either because the magnetic field temporarily weakens, choking off the particle supply, or because charged particles from the interstellar medium flood the magnetosphere, short-circuiting the beam mechanism. Think of it like a hydroelectric dam. If the water flow drops too low, the turbine stops spinning until the reservoir refills. Another possibility points to precession, a slow wobble in the pulsar's spin axis. If the neutron star's rotation isn't perfectly aligned, its beams might sweep across space like a wobbling top, sometimes pointing toward Earth, sometimes away. But this doesn't fully explain the abruptness of the transitions or the precise timing of the cycles. There's also the wild card of an unseen companion, perhaps a debris disk or a faint star, that periodically disrupts the pulsar's magnetosphere like a cosmic dimmer switch. What's truly unsettling is how these quiet periods affect the pulsar's spin. When active, Pulsar B 1931 plus 24 slows down at a rate typical for its age. But during its off phases, the braking effect decreases by about 50%, suggesting that the beams aren't just silent, they've genuinely ceased, halting the energy loss tied to their radiation. This duality implies that pulsar slowdown isn't solely due to internal processes. The act of beaming itself plays a crucial role in sapping the star's rotation. The zombie pulsar isn't alone in this strange behavior. A handful of others, like Pulsar J 1840-0525, exhibit similar on-off cycles, hinting at an unknown subclass of neutron stars operating by different rules. Some even speculate these objects might be connected to fast radio bursts, those millisecond cosmic flashes whose origins remain debated. Could intermittent pulsars be FRBs in disguise, their off states building up energy for explosive releases? For now, Pulsar B 1931 plus 24 keeps its secrets, shifting between silence and song with no discernible pattern. Each time it vanishes, astronomers are left wondering if it'll return, or if this time the zombie will stay dead. Its very existence reminds us that even the most predictable cosmic clocks can harbor mysteries, and that somewhere in the dark, the universe is still writing rules we've yet to understand. There's something hauntingly beautiful about listening to the universe's pulse, not as data points on a graph, but as sound. Scientists have found a way to translate the radio waves emitted by pulsars into audio, transforming their rhythmic flashes into eerie, otherworldly melodies. The process, called sonification, takes the precise intervals between pulses and shifts them into frequencies the human ear can perceive. What emerges isn't just noise, it's a symphony of cosmic heartbeats, each pulsar singing its own unique song. Take Pulsar B 0329 plus 54, for example. When its radio waves are converted, it produces a deep, resonant thumping almost like a bass drum, steady as a metronome. Others, like the millisecond pulsar Pulsar J 0437-4715, create rapid, staccato clicks that blur together into a high-pitched whir, like a watch ticking at hyperspeed. These sounds aren't just for ambience, they're tools for discovery. Astronomers often detect subtle irregularities in pulsar timing by ear long before algorithms flag them. A slight waver in the rhythm, an extra click where there shouldn't be, these auditory clues have led to the discovery of planetary companions, gravitational wave disturbances, and even glitches in a pulsar's spin. The Vela pulsar, for instance, famously stutters in its audio translation. its steady beat occasionally interrupted by a telltale hiccup that revealed internal starquakes. But there's an artistic dimension too. Some pulsar sounds have been woven into musical compositions, their natural rhythms providing the backbone for experimental pieces that bridge science and art. The collaboration between astrophysicists and musicians has even produced albums where distant neutron stars duet with violins and synthesizers, turning hard data into something visceral and emotional. What's most striking is how familiar these cosmic beats feel. Strip away the interstellar origins, and many pulsar recordings echo the pulse of a human heart, the creak of old floorboards, or the static hiss of a vinyl record. It's a reminder that the universe isn't just something we see, it's something we can hear, a hidden soundtrack woven into the fabric of space itself. And every time we press play on these pulsar soundscapes, we're not just observing the cosmos, we're letting it speak to us. Somewhere between a pulsar's steady pulse and a magnetar's violent eruptions lies a cosmic shape-shifter, a neutron star caught in the act of becoming something else entirely. Astronomers call these rare objects missing link pulsars, and stumbling upon one is like catching a butterfly mid-metamorphosis. Take Pulsar J1119-6127, a pulsar discovered in 2016 that defies classification. At first glance, it ticks like any other rotation-powered pulsar, its beams fueled by the energy of its rapid spin. But then, without warning, it erupts in bursts of X-rays and gamma rays, behavior typical of magnetars, neutron stars with magnetic fields 1,000 times stronger than ordinary pulsars. This hybrid nature makes it one of the rarest astrophysical discoveries, a pulsar actively transitioning between two states, offering a front-row seat to stellar evolution in real time. What makes this transformation possible lies in the pulsar's decaying magnetic field. Most magnetars are thought to be born from supernovae so violent they twist the neutron star's magnetic field into knots, creating intensities strong enough to rip atoms apart. Over tens of thousands of years, that field gradually weakens, and the magnetar settles into a quieter life as a rotation-powered pulsar. But Pulsar J1119-6127 appears to be straddling the midway point. Its magnetic field, while still formidable, has decayed enough to allow regular pulsar activity except when it suddenly flares up, unleashing magnetar-like outbursts that can outshine the star's steady pulses by a factor of 100. The clues to this duality are etched in its light. During quiet periods, its X-ray emissions match those of a typical middle-aged pulsar. But when it flares, the energy spectrum shifts dramatically, revealing the telltale signature of magnetic reconnection, a process where magnetic field lines snap and reconnect, releasing explosive energy. These outbursts aren't just dim flickers. One observed event in 2017 lasted nearly 2 months, during which the pulsar's X-ray luminosity jumped by a staggering 300 times. It's as if the star can't decide which identity to embrace, flickering between personalities like a celestial Jekyll and Hyde. Why this matters goes beyond mere classification. Missing link pulsars could finally answer one of neutron star astronomy's biggest debates. Are magnetars a distinct class of objects or just a phase all pulsars go through? If pulsars like Pulsar J1119-6127 are common, it suggests that magnetar behavior might be a temporary adolescent phase in a neutron star's life cycle. But if they're exceedingly rare, it implies that only stars born under special conditions, perhaps with unusually rapid rotation or asymmetric supernova, ever develop magnetar-level magnetic fields. The implications ripple outward. These transitional objects might also explain mysterious phenomena like fast radio bursts. Some theorists speculate that the magnetic turmoil during a pulsar's shift to magnetar status could generate the precise conditions needed for those millisecond cosmic flashes. Others suggest that switching pulsars could be the source of sporadic gamma-ray signals that have puzzled astronomers for decades. For now, Pulsar J1119-6127 remains an enigma, its dual nature resisting easy explanation. Every flare, every pulse, every moment of silence is a clue, a piece of a puzzle that could rewrite how we understand the lives and deaths of the universe's most extreme objects. And as telescopes grow more sensitive, who knows how many other celestial chameleons are out there, hiding in plain sight, waiting to blur the lines we've drawn between the cosmos's most violent and orderly phenomena. Long before scientists decoded their cosmic rhythms, pulsars were already firing the human imagination not as celestial oddities, but as plot devices in some of science fiction's most iconic stories. Take the climactic scene in Carl Sagan's Contact, where the protagonist Ellie Arroway discovers an alien transmission hidden in the pulsars of Vega's neutron star. The novel, and later the film, got one thing startlingly right. Pulsars really are nature's perfect carriers for interstellar messages. Their precise beats could theoretically encode vast libraries of information, just as Sagan envisioned. In fact, the very first pulsar discovered, CP 1919, was briefly nicknamed LGM for Little Green Men, because its unnatural regularity had astronomers half convinced they'd stumbled upon an extraterrestrial beacon. But Pulsar's pop culture influence runs deeper. Doctor Who fans might remember the Castorborous Pulsar cluster, the fictional constellation marking the Time Lord homeworld Gallifrey. The show's writers borrowed a real cosmic phenomenon, pulsar timing arrays, to explain how the Doctor's TARDIS navigation works, treating spinning neutron stars as galactic signposts. Even Transformers got in on the action with the 1986 animated movie featuring a pulsar planet whose crushing gravity threatened the Autobots, a nod to neutron stars' real-world ability to warp spacetime. These fictional portrayals often exaggerate, but sometimes they eerily predict. Star Trek's subspace communications mirror real proposals to use pulsars as quantum entanglement relays for faster-than-light messaging. And when Interstellar's crew navigated a black hole using gravitational beaconing, they were essentially mimicking how spacecraft might one day triangulate positions using pulsar X-rays. What makes pulsars such compelling storytelling devices is how they blur the line between science and myth. Their pulses resemble Morse code, their extreme physics feels alien, and their sheer age connects them to the universe's primordial past. No wonder they've been depicted as everything from alien homing devices The X-Files to cosmic bombs Green Lantern. Behind every fictional pulsar trope lies a kernel of truth, a testament to how reality can inspire tales stranger than fiction. And as our understanding of these stellar lighthouses grows, so too will their role in the stories we tell about the cosmos and our place within it. Around certain pulsars, the cosmos paints with light, vast, luminous clouds called pulsar wind nebulae that stretch for light years, glowing with energies that outshine entire star clusters. The most famous of these, the Crab Nebula, is a celestial masterpiece, a tangle of filaments and energetic haze born from a supernova witnessed on Earth in 1054. At its heart lies the Crab Pulsar, spinning 30 times per second, its furious winds of charged particles inflating the nebula like a cosmic balloon. What we see isn't just remnants of an explosion, it's a living structure, continuously energized by the pulsar's relentless output. These nebulae form when a pulsar's magnetic field accelerates particles to near light speed, creating a storm of electrons and positrons that slam into surrounding gas. The result is a cascading light show. X-rays from the highest energy collisions, visible light from excited atoms, and radio waves tracing the nebula's magnetic skeleton. The Vela Pulsar's nebula, for instance, resembles a ghostly hand spanning 100 light-years, its delicate tendrils glowing from particles that began their journey when dinosaurs still roamed Earth. But pulsar wind nebulae aren't just pretty, they're particle accelerators on a galactic scale. The Crab's Nebula alone generates energies 1,000 times beyond what humanity's largest colliders achieve, offering clues about how cosmic rays' mysterious high-energy particles bombarding Earth are born. Some, like G0.2 plus 0.9 near the Milky Way center, even reshape their surroundings, carving bubbles in interstellar gas that serve as cosmic petri dishes for star formation. The real magic lies in their evolution. Young pulsars like the Crab power tight, bright nebulae, while older ones, such as the Mouse Nebula trailing PSRB 1757-24, stretch into comet-like tails as they plow through space. A few, like the bizarre donut of SNRG 0.9 plus 0.1, even flicker as their pulsars undergo outbursts, proving these structures are anything but static. Each nebula is a cosmic fingerprint, its shape revealing the pulsar's spin, magnetic field, and even its motion through space. They're reminders that even in death, stars don't fade quietly. They ignite new forms of brilliance, turning their final acts into some of the universe's most dazzling performances. If you think pulsars are strange, wait until you meet IGRJ1 1014-6103, a cosmic renegade that doesn't just spin, it sprints. Racing through space at over 5 million miles per hour, this pulsar isn't content with merely flashing its beams. It's carving a path through the galaxy with a collimated jet stretching 37 light-years behind it like a fiery wake. To put that in perspective, if this jet were placed in our solar system, it would stretch from the Sun to twice the distance to the nearest star. What could possibly propel a neutron star with such reckless speed, while simultaneously firing a particle beam longer than most star-forming regions? The answer is written in the wreckage of a supernova explosion so violent, it didn't just birth a pulsar, it launched it like a bullet from a cosmic gun. This pulsar's origin traces back to the supernova remnant LMC N159, where the death throes of a massive star weren't symmetrical. Most supernova eject material evenly, leaving behind a neutron star with a modest kick. But IGRJ1 1014-6103 got a lopsided detonation, its shockwaves funneled in one direction like thrust from a rocket nozzle. The result, a neutron star catapulted into space with enough force to escape its own galaxy, dragging along a twisted helix of magnetic fields that now powers its incredible jet. The jet itself is a masterpiece of particle acceleration, electrons spiraling along magnetic field lines at nearly light speed, glowing in X-rays as they collide with interstellar gas. What baffles scientists isn't just the jet's length, but its structure. Unlike typical pulsar jets, which are straight and narrow, this one spirals like a corkscrew, evidence of the pulsar's wobbling spin as it tumbles through space. The jet also pulses independently of the neutron star's rotation, suggesting hidden dynamics in its magnetic field or interactions with debris left over from the supernova. Some theorists speculate the jet might even be pumped by the pulsar's motion, like a garden hose whipping through the air, its stream bending unpredictably. The real astonishment comes when you realize this system breaks multiple astrophysical rules. Jets this long are usually associated with black holes, not neutron stars. Yet here's IGRJ1 1014-6103 defying expectations, its existence forcing us to reconsider how particles are accelerated in extreme environments. It's as if the universe took every textbook chapter on compact objects and tossed them out the window. For astronomers, this pulsar is a goldmine. Its jet acts like a cosmic particle detector, illuminating the otherwise invisible magnetic fields threading through interstellar space. The pulsar's speed offers clues about supernova mechanics, hinting at how much energy can be channeled into a single directional kick, and its very persistence, surviving while hurtling through gas clouds that should disrupt the jet, suggests neutron stars might be far more resilient than we thought. As it streaks toward the void between galaxies, IGRJ1 0.1014-6103 leaves behind more than just a glowing trail. It's a challenge, a reminder that even the most extreme objects we've discovered might just be the tip of the cosmic iceberg, and somewhere out there, another celestial rebel is waiting to rewrite the rules all over again. To grasp the sheer power of a pulsar's magnetic field, picture an ordinary refrigerator magnet, then multiply its strength by 100 trillion. That's the mind-numbing intensity we're dealing with. Forces so strong they don't just bend the rules of physics, they shatter them. At their peak, these fields reach 10 to the 15th Gauss, numbers so large they lose meaning, until you realize Earth's protective magnetic shield measures a modest half Gauss by comparison. It's the difference between a gentle breeze and a hypercane capable of shredding atoms. Consider modern medicine's most powerful MRI machines, which operate at about 3 Tesla, roughly 60,000 times Earth's magnetism. Now imagine a machine 60 billion times stronger than that. At these extremes, the laws of quantum electrodynamics warp. Electrons spiral along magnetic field lines at nearly light speed, emitting synchrotron radiation so intense it can ionize molecules light years away. This isn't just strong, it's rip electrons from atoms at a distance strong, rearrange the periodic table strong. The real terror begins when these fields interact with matter. White dwarf stars themselves dense enough to crush a person into a sugar cube-sized speck would be torn apart like tissue paper in a pulsar's magnetosphere. Even light bends under these conditions, with X-rays polarized into eerie, spiraling patterns. Some magnetars, the most magnetic pulsar variants, generate starquakes when their crusts rupture under magnetic stress, releasing bursts of energy equivalent to 100,000 suns in a millisecond. Yet paradoxically, these fields also create cosmic art. The Black Widow Pulsar PSRB 1957+20 uses its magnetism to sculpt its evaporating companion into a glowing, comet-like tail. Other pulsars generate auroras on nearby planets that would put Earth's northern lights to shame if any atmosphere could survive the particle bombardment. What makes these fields even more astonishing is their origin. During a supernova collapse, the progenitor star's magnetic field gets compressed along with its matter. As the core shrinks from the size of a city to a village, the field lines are squeezed together, amplifying their strength exponentially, like taking a bar magnet and folding it over and over until its atomic scale. This process, called flux conservation, turns what was once a stellar magnetic field into a cosmic particle accelerator. The practical implications are staggering. If such fields could be replicated on Earth, they'd revolutionize energy production, allowing fusion reactors to contain plasma at sun core temperatures. Of course, the same forces that make them useful would also make them lethal. A pulsar-strength magnetic field at 1 kilometer would erase credit cards, liquefy pacemakers, and potentially stop a human heart through induced electrical currents. Yet in the grand tapestry of the cosmos, these unimaginable forces serve a purpose. They shape pulsar winds, power particle jets, and even influence galaxy-scale magnetic fields. Every pulse we detect carries encrypted data about these invisible behemoths, reminding us that the universe's most powerful forces often leave no visible trace until something gets in their way. At the heart of the constellation, Cassiopeia spins a cosmic oddity so sluggish it shouldn't exist. Pulsar J0250+5854, a pulsar that takes a leisurely 23.5 seconds to complete a single rotation. That might not sound impressive until you realize most pulsars spin hundreds of times faster in that same time frame. This lethargic neutron star is the universe's equivalent of a record player stuck on the slowest setting, its languid pulses challenging everything we thought we knew about how these objects behave. The mystery lies in its very existence. Pulsars are born spinning rapidly from the collapse of massive stars, their rotations fueled by the conservation of angular momentum, the same physics that makes an ice skater spin faster when they pull their arms in. Conventional wisdom says they should never slow to such a crawl so early in their lives. At just 16,000 years old, a toddler by cosmic standards, Pulsar J0250 plus 5854 spins slower than 99% of known pulsars, some of which are hundreds of millions of years older. It's as if astronomers found a teenager with the heartbeat of a hibernating tortoise. What could possibly explain this anomaly? One theory suggests it might be the descendant of an entirely different class of star, a magnetar, the supermagnetic cousin of pulsars. Magnetars are known to have powerful magnetic fields that break their rotation aggressively. If this pulsar began life as a magnetar whose field decayed over time, its sluggish spin could be the fossil record of that earlier, more ferocious phase. Observations reveal another clue. Its magnetic field, while not magnetar strength, is still 10 times stronger than most ordinary pulsars, lending credence to the magnetar ancestry hypothesis. But there's a catch. Even with a strong magnetic field, models struggle to explain how it slowed this dramatically without simply shutting off. Pulsars typically cease emitting detectable beams when their rotations drop below once every few seconds. Pulsar J0250 plus 5854 somehow keeps pulsing past that limit, its beams defying the usual death knell for radio emission. Some researchers speculate it might be feeding off residual heat from its interior or drawing energy from an unseen debris disk left over from its supernova. The discovery, made in 2018 by the Low Frequency Array Radio Telescope, almost didn't happen. Its long period means most pulsar surveys would have dismissed its signal as interference. Radio telescopes are typically tuned to catch millisecond flickers, not half-minute sweeps. It was only through careful reanalysis of older data that astronomers spotted its steady, slow pulse hiding in plain sight. Now, it's rewriting textbooks on neutron star evolution, proving that the universe always has room for outliers that refuse to follow the rules. What makes this cosmic slowpoke invaluable is what it reveals about pulsar diversity. Before its discovery, astronomers assumed all neutron stars followed a predictable spin-down trajectory. Now they're questioning whether there's an entire population of slow-spinning pulsars we've missed, their languid rhythms overlooked in our haste to catalogue the fastest and brightest. Future telescopes like the Square Kilometre Array might uncover dozens more, painting a far richer picture of how these stellar corpses age. For now, Pulsar J0250 plus 5854 continues its solitary waltz, each lazy rotation a reminder that even the most extreme objects in the universe can surprise us. In a cosmos obsessed with speed, it's content to take its time, and in doing so, it's teaching us more about the quiet, overlooked chapters of a neutron star's life than we ever expected to learn. Some of the most distant pulsars we detect aren't just faraway objects, they're time travelers. They're signals carrying whispers from the universe's infancy. When we observe a pulsar located billions of light years away, we're not just seeing light that's old. We're glimpsing a snapshot of the cosmos as it existed before Earth, before the Milky Way, even before most galaxies had finished forming. These signals have journeyed across epochs, passing through primordial gas clouds and warping around gravitational wells, each interaction leaving subtle fingerprints that tell the story of how the universe grew up. Take Pulsar J0146 plus 6145, one of the most distant pulsars ever discovered. Its pulses have traveled for nearly 6 billion years to reach us, meaning they began their journey when the universe was less than half its current age. Along the way, those pulses passed through regions of space that were still rich with hydrogen from the Big Bang before stars had fully ionized the cosmos. By analyzing how those ancient hydrogen clouds absorbed specific frequencies in the pulsar's signal, astronomers reconstructed the chemical makeup of the early universe, confirming theories about how the first elements formed. But the echoes go deeper. Some pulsar beams have traversed vast cosmic voids, regions where gravity has pulled matter away, leaving behind near-empty bubbles in spacetime. As these beams skim the edges of these voids, their paths curve ever so slightly, an effect called gravitational lensing. By mapping these distortions in pulsar signals, scientists can weigh the invisible, dark matter filaments threading between galaxies or rogue black holes drifting unseen. It's like using the pulsar as a flashlight to illuminate the invisible scaffolding of the cosmos. The most extraordinary echoes come from pulsars whose light has interacted with the cosmic microwave background, the afterglow of the Big Bang itself. In 2022, researchers studying Pulsar J0740+662 noticed minuscule shifts in its polarization, the orientation of its radio waves, caused by collisions with photons from the early universe's cooling plasma. These subtle imprints, called Sachs-Wolf signatures, act like cosmic weather reports, revealing temperature fluctuations in the infant universe with staggering precision. What makes these distant pulsars indispensable is how they fill gaps in our cosmic timeline. The first few 100 million years after the Big Bang, often called the Dark Ages, remain frustratingly opaque to conventional telescopes. No stars had formed yet, leaving no light to study except potentially the beams of pulsars that flared to life during that era. While we haven't found one quite that old yet, theorists suggest their existence could one day let us peer into that shadowy epoch directly, like finding a candle that somehow stayed lit in a prehistoric cave. Every pulse from these cosmic elders is a message in a bottle cast across time. They carry evidence of the universe's first magnetic fields, traces of its initial expansion rate, even clues about whether the fundamental constants of physics have changed over billions of years. And with each new distant pulsar discovered, we add another piece to the puzzle, not just of how the universe works today, but how it became what it is, one pulse at a time. There's a pulsar in the constellation Sagittarius that refuses to die, even as its own radiation slowly vaporizes its companion star. Pulsar B1957+20, nicknamed the Black Widow Pulsar, is a cosmic survivor locked in a lethal embrace with its binary partner, a star roughly 1% the mass of our Sun. What makes this system extraordinary isn't just its violence, but the pulsar's ability to endure conditions that should have torn it apart. Its companion orbits so close that tidal forces from the neutron star's gravity distort it into a teardrop shape, while particle beams and gamma rays blast away its outer layers at a rate of 1 Earth mass every million years. Yet through it all, the pulsar pulses on, unfazed by the carnage it's unleashing. This deadly dance offers a front-row seat to astrophysical extremes. The companion star's sunward side is heated to over 12,000 degrees Celsius, twice as hot as our Sun's surface, while its shadowed side remains eerily cool, creating a temperature gradient that rips atoms apart. The escaping gas forms a comet-like tail stretching over 20 astronomical units, visible in ultraviolet as a shimmering wake of destruction. But here's the twist: the pulsar doesn't just destroy its partner, it feeds on it. Some of the stripped material gets caught in the pulsar's magnetic field, funneled onto its surface in violent accretion streams that generate additional X-ray emissions. It's a self-sustaining cycle of annihilation and renewal, where the star's death throws power the very object killing it. What's truly baffling is how the system remains stable. Conventional models predict such tight binaries should either merge or disrupt within millennia. Yet Pulsar B1957+20 has persisted for millions of years. The secret might lie in equilibrium. The companion star is just massive enough to replenish the pulsar's energy lost through accretion, but not so massive that it's quickly obliterated. It's a cosmic balancing act, like a vampire carefully draining its victim to keep the blood supply flowing. The pulsar's resilience extends to its own structure. Theorists once thought such intense radiation feedback would destabilize its magnetic field or trigger erratic spin changes. Yet its pulses arrive with metronomic precision, varying by less than a microsecond over decades. This stability suggests its internal dynamics, possibly a superfluid neutron core, act as a shock absorber, smoothing out disturbances that would fracture lesser stars. But the most tantalizing clue lies in what's left behind. As the companion star dwindles, it's evolving into something entirely new. A helium-rich remnant no larger than Jupiter, yet dense enough that its carbon core may crystallize into diamond under the crushing pressure. Future telescopes might one day catch this system in its final act, a glittering diamond planet orbiting the pulsar that created it, a tombstone forged from destruction. PSRB 1957+20 isn't just a celestial oddity. It's a time capsule of stellar evolution, proving that even in death, stars can create wonders. And somewhere in the galaxy, another black widow is spinning up, its lethal waltz just beginning. While atomic clocks on Earth are marvels of precision, they have an Achilles heel. They rely on human-made systems that degrade over time. Pulsars, on the other hand, are nature's answer to eternal timekeeping. These spinning neutron stars have maintained their rhythmic pulses with near-perfect stability for millennia, and they'll likely continue doing so long after our most advanced atomic clocks have fallen silent. Unlike terrestrial timekeepers, which depend on delicate quantum transitions in cesium or rubidium atoms, pulsars are powered by the relentless laws of physics conservation of angular momentum and the incomprehensible density of neutron star matter. Their beats are so reliable that over decades of observation, some millisecond pulsars rival the precision of atomic clocks, losing or gaining less than 1 second every 10 million years. The real advantage of pulsar timekeeping lies in its longevity. Atomic clocks, no matter how advanced, require maintenance, power, and protection from environmental interference. A single catastrophic event, a solar flare, a global conflict, or even simple neglect could silence them forever. Pulsars, by contrast, are virtually indestructible. Their rotations are unaffected by cosmic disasters, their energy drawn from the slow, inevitable bleed of rotational momentum. Even as the universe ages and galaxies drift apart, these cosmic metronomes will keep ticking, their pulses echoing across the void long after human civilization has faded from memory. This endurance makes them ideal for deep time projects. Imagine a future where interstellar spacecraft or long-term archives use pulsar signatures as their internal clocks, synchronizing across light years without needing Earth-based updates. The Voyager Golden Record already includes pulsar maps as a cosmic "you are here" marker for any aliens who might find a testament to their reliability as universal timestamps. Some scientists have even proposed creating a pulsar time standard, a celestial network where multiple pulsars act as redundant timekeepers, cross-verifying each other to compensate for individual anomalies like glitches or gravitational wave disturbances. But pulsar timekeeping isn't just about durability, it's about perspective. Atomic clocks measure time in human terms, tied to Earth's rotation and our planet's tiny slice of cosmic history. Pulsars operate on galactic timescales, their rhythms indifferent to our calendars or time zones. By syncing to them, we're not just keeping time, we're aligning ourselves with the universe's heartbeat, stepping outside our fleeting moment to embrace a chronology that stretches from the Big Bang to the heat death of everything. Their pulses are more than signals, they're a bridge across epochs, a way to anchor our ephemeral now to the infinite. Of course, challenges remain. Pulsar signals weaken over interstellar distances, and subtle timing variations can arise from the interstellar medium's electron clouds. Yet advanced algorithms and next-generation telescopes like the Square Kilometre Array are already overcoming these hurdles, refining pulsar timing to unprecedented accuracy. The dream isn't just to match atomic precision, it's to surpass it, creating a clock that never needs winding, a timepiece built into the fabric of spacetime itself. So while atomic clocks may rule our labs and satellites today, the future of timekeeping might not lie in a vault in Paris or a satellite in orbit. It might be written in the stars, in the unfaltering spin of dead suns that outlast civilizations, outlast planets, and perhaps one day outlast time itself. Deep in the galactic plane, an enigmatic object refuses to play by the rules. Gleam XJ162759.5, a cosmic strobe light flashing with eerie precision every 18 minutes. Unlike any known pulsar, this ghostly beacon emits bursts of radio waves so powerful they briefly outshine entire galaxies, then vanishes without a trace. Discovered in 2022 by astronomers scanning old telescope data, this celestial oddity has sparked a firestorm of debate. Is it a pulsar pushing the limits of physics, an entirely new class of object, or something even stranger? What makes Gleam X so baffling is its rhythm. Pulsars typically flash anywhere from milliseconds to a few seconds. Some millisecond pulsars spin hundreds of times per second like hyperactive cosmic tops. But 18 minutes, that's longer than the slowest known pulsar by a factor of 1,000. Yet its emissions bear the hallmarks of neutron star activity, polarized radio waves and a spectrum suggesting synchrotron radiation, where electrons spiral around magnetic field lines at near light speeds. If it is a pulsar, its magnetic field would need to be unusually weak, allowing it to spin so leisurely without shutting off entirely. But here's the twist: Gleam X's pulses aren't just slow, they're erratic in ways that defy conventional models. Instead of the steady, metronomic beats of a typical pulsar, it bursts very wildly in brightness, sometimes disappearing for cycles before returning at full strength. This behavior resembles magnetars, neutron stars with apocalyptic magnetic fields, except magnetars don't usually pulse with such clockwork regularity. Some theorists propose a hybrid scenario, a magnetar transitioning into a pulsar, its decaying magnetic field enabling slower rotation while still permitting violent outbursts. Then there's the distance mystery. Unlike most pulsars whose dispersion measures give clear clues about their location, Gleam X's signal shows minimal scattering from interstellar electrons, suggesting it's relatively close, possibly within our galactic neighborhood. Yet no known supernova remnant or neutron star candidate exists at its suspected location. It's as if this object materialized out of nowhere, a cosmic ghost with no trace of its violent birth. The most radical explanations venture beyond neutron stars entirely. Could this be a white dwarf pulsar? These dense stellar remnants can produce radio emissions, but none have ever been observed with periods longer than a few minutes. Alternatively, might it be a blitzar, a hypothetical neutron star that narrowly avoided collapsing into a black hole, leaving behind a suspended, unstable remnant? Or is there some entirely unknown astrophysical phenomenon at work, a celestial mechanism we've yet to imagine? For now, Gleam X remains an enigma, its true nature hidden behind layers of cosmic static. But its very existence is a gift to science, a reminder that even in an era of advanced telescopes and AI-assisted discovery, the universe still holds puzzles that defy our categories. Every flicker from this ghostly beacon is a challenge, a dare to rethink what we know about the life and death of stars, and somewhere in its cryptic pulses may lie the key to unlocking not just its own identity, but new chapters in our understanding of the cosmos itself. Deep within a pulsar's core, matter doesn't just behave strangely, it defies reality as we know it. Here, crushed under pressures 100 trillion times greater than Earth's oceans, neutrons abandon all resistance and transform into a superfluid, a quantum state where particles move in perfect, frictionless sync, as if the universe itself hit mute on the chaos of physics. Imagine pouring a cup of liquid that flows uphill, climbs walls, or never loses energy to heat. and you're barely scratching the surface of how bizarre this phenomenon truly is. The key to this cosmic wizardry lies in the extreme conditions inside neutron stars. At these densities, the space between atomic nuclei vanishes entirely, leaving neutrons packed shoulder to shoulder in a sea governed by quantum mechanics rather than classical physics. Normally, neutrons repel each other fiercely, but under pulsar-level pressures, something extraordinary happens. They pair up like dancers in a cosmic ballet, forming what scientists call Cooper pairs. These pairs unlock the superfluid state, allowing neutrons to flow without viscosity, meaning zero energy loss, zero turbulence, and zero friction. It's as if the pulsar's interior becomes the universe's most efficient engine, humming silently with perfect efficiency. But the real magic happens when this superfluid interacts with the pulsar's rigid crust. While the outer shell of the neutron star rotates as a solid, the superfluid core can spin independently, creating a celestial tug of war. When the crust slows down due to magnetic braking, the process that saps a pulsar's rotational energy over time, the superfluid's vortices, tiny quantum whirlpools, suddenly unpin and surge outward, transferring angular momentum to the crust in a violent jolt. This is the hidden mechanism behind pulsar glitches, those sudden speed-ups in spin that baffled astronomers for decades. The Vela pulsar, for instance, famously glitches every few years, its rotation abruptly spiking by 1 part in a million, all because its superfluid core just gave the crust a gravitational kick. Superfluidity doesn't just explain glitches, it reshapes our understanding of matter itself. In Earth labs, superfluids like liquid helium-4 exhibit surreal behaviors, creeping up glass walls, dripping through impossibly small pores, or forming quantum vortices that last indefinitely. But pulsar superfluids are orders of magnitude more extreme. Their neutron pairs likely exist in a 3p2 configuration, a high-energy state where particles align in complex anisotropic patterns predicted by theory but impossible to replicate on Earth. Some models even suggest layers of proton superconductivity coexist with neutron superfluidity, creating a pulsar core that's part superfluid, part superconductor, and entirely alien to human experience. The implications ripple far beyond neutron stars. If superfluidity can persist for millions of years in pulsars, it hints at quantum coherence on macroscopic scales, a phenomenon that could revolutionize technologies like quantum computing or energy storage. There's even speculation about quark superfluids deeper in the core, where neutrons dissolve into quark-gluon plasma, potentially forming color superconductors that generate the strongest magnetic fields in the universe. Yet for all its strangeness, pulsar superfluidity isn't just theoretical. Observations of cooling neutron stars provide indirect evidence. Younger pulsars shed heat too quickly for ordinary matter, matching models where superfluidity enhances neutrino emissions. The Cassiopeia, a supernova remnant neutron star, for example, cooled by 4% in a decade, unnosed, only explainable by superfluid neutrons pairing up and releasing a flood of ghostly neutrinos. This quantum dance inside pulsars is more than a curiosity, it's a masterclass in nature's ingenuity. Under conditions we can scarcely imagine, matter reaches into its bag of tricks and pulls out states that seem ripped from science fiction. And every glitch, every pulse, every whisper of radiation carries encoded hints about this hidden realm, reminding us that the universe's most exotic physics often plays out in the hearts of its most extreme objects. Right now, scattered across remote deserts and quiet plains, an astronomical revolution is taking shape, not in the stars but here on Earth. The Square Kilometre Array, or SCAR, isn't just another telescope. It's a sprawling network of hundreds of radio dishes and thousands of antennae spanning 2 continents, designed to listen to the cosmos with unprecedented sensitivity. When fully operational in the late 2030s, this megaproject will transform pulsar hunting from meticulous discovery to a firehose of data, uncovering thousands of these cosmic lighthouses, some so distant their light predates the formation of our solar system. What makes SK a game-changer isn't just its size, though with a total collecting area of, yes, 1 square kilometer. It's the largest radio telescope ever conceived, but its technological wizardry. Its dishes in South Africa and Australia will work in concert, creating a virtual telescope so precise it could detect a mobile phone signal on a planet orbiting a star tens of light years away. For pulsars, this means catching whispers from the far edge of the observable universe, signals so faint they've slipped through every other telescope's grasp. Early tests with SK precursors have already teased this potential. In 2023, a pilot array discovered a pulsar 15,000 light-years away buried in noise that would have been invisible to older instruments. But SK's real power lies in its speed. Current pulsar surveys might discover a few dozen candidates per year. SK could spot that many in a single day. Its supercomputers, processing data equivalent to the entire internet's traffic every second, will sift through cosmic static in real time, flagging anomalies human eyes might miss. This deluge of discoveries promises to fill glaring gaps in our knowledge, like the mysterious absence of pulsars with periods between 1 and 10 milliseconds, a gap that could reveal new physics about neutron star formation. There's even hope it might find the Holy Grail, a pulsar orbiting a black hole, a pairing that would let us test Einstein's general relativity under conditions of extreme gravity. And then there's the dark horse of next-gen observatories, the 500-meter aperture spherical telescope, or FAST, nestled in China's karst mountains. Already holding the record for the most pulsars discovered in a single survey, FAST dish large enough to hold 30 football fields is so sensitive it can detect the faintest rotational slowdown in distant pulsars, a key to unlocking their internal composition. Combined with SKA, these telescopes will create a golden age of pulsar astronomy, mapping the Milky Way's spiral arms in unprecedented detail and potentially uncovering exotic varieties we've only theorized, like quark stars or pulsars encased in dark matter halos. The data won't just answer old questions, it'll pose new ones. Every distant pulsar SKA finds is another tick mark in a cosmic census, revealing patterns in their distribution that could explain why some galactic regions are eerily devoid of neutron stars while others glitter with them. Some theorists speculate we might even find pulsars orbiting primordial black holes from the early universe, or ones flung into intergalactic space by ancient supernovae so powerful they escaped their home galaxies entirely. Yet the most thrilling possibility is one we can't yet imagine. Every time humanity has built a telescope with a new level of sensitivity, it's stumbled upon phenomena that rewrite textbooks: radio galaxies, quasars, fast radio bursts. SKA and its peers will likely do the same, uncovering pulsars that pulse in ways that defy current models, or that reside in places we thought impossible. These discoveries won't just fill databases, they'll redefine what we know about matter, gravity, and the life cycles of stars. So while today's pulsar hunters work with patience and luck, their successors will wield tools so powerful that the universe's most precise clocks will have nowhere left to hide. And when that flood of data arrives, we may find that pulsars, these seemingly simple spinning stars, have been keeping more secrets than we ever dreamed. From the farthest reaches of the cosmos to the quantum chaos inside a neutron star's core, pulsars have taken us on a journey that stretches the limits of imagination. These 30 astonishing facts reveal why these cosmic lighthouses are more than just celestial oddities. They're keys to unlocking the universe's deepest secrets. We've seen pulsars racing through space at millions of miles per hour, their supersonic wakes carving glowing trails across the galaxy. We've marveled at their precision, keeping time more reliably than any human-made clock, while their erratic glitches betray the surreal superfluid oceans churning beneath their crusts. Some whisper to us from the edge of the observable universe, their pulses encoding messages from when galaxies were newborn. Others devour their stellar companions in lethal embraces or hurl diamond planets through the void. They challenge everything we thought we knew about physics. Pulsar wind nebulae act as particle accelerators dwarfing anything on Earth, while their gravitational wave hum could rewrite Einstein's theories. Their cores might harbor quark matter, a state of existence unseen since the Big Bang's first moments. And lurking in the darkness are enigmas like the zombie pulsar that vanishes for years, or the slowest spinner defying all models of stellar decay. Each discovery peels back another layer, revealing how much we still don't understand about matter, time, and the forces shaping reality itself. But here's the most beautiful part: this is just the beginning. With telescopes like the Square Kilometre Array coming online, we're on the brink of uncovering pulsars that could shatter today's theories. Maybe we'll find one orbiting a primordial black hole, or detect a beam encoded with signs of dark matter. Perhaps the ultimate cosmic messenger is already pulsing toward us, carrying truths we're not yet equipped to decode. Now it's your turn. What fact left you awestruck? Was it the diamond planet, the hypervelocity jets, or the pulsar that might unravel space-time itself? Drop your favorite cosmic mystery in the comments, and let's keep the conversation as boundless as the stars. Because the universe isn't just stranger than we imagine, it's stranger than we can imagine, and pulsars are proof. So keep looking up, stay curious, and remember, every pulse out there is a reminder that the cosmos still has stories left